Hello everyone, I'm Jiansheng from Harbin Institute of Technology Shenzhen. Since the author cannot present their paper due to visa issue, I'm here to present instead. The talk is HotRAP, Hot Record Retention and Promotion for LSM-trees with tiered storage. First, I'd like to introduce LSM-trees with tiered storage. To put a key value pair into the LSM-tree, we first insert it into the mutable memory table. After the mutable memory table gets full, it is converted into an immutable memory table. Then, the immutable memory table will be flushed into the first level in the fast disk. When a level becomes full, compactions are triggered to merge its data into the next, larger level. To get the value of a key, we first check the mutable memory table, then the immutable memory tables, followed by the levels on disk, until we find the corresponding value. As we can see, recent records are stored in upper levels, and the upper levels, for example, L1 and L2, are stored in the fast disk. In many scenarios, recent records are also hot, so those hot records are naturally stored in the fast disk, and reading them is fast. However, hot records may stay hot for a long time, but they inevitably sink into the slow disk, and reading them becomes slow. So, a natural question is that, can we keep hot records in the fast disk? There are already some works addressing this problem. To better understand these works, we need to know what SS tables and blocks are. First, all keys in each level, for example, L1, are sorted from smallest to largest. And each level consists of SS tables, and each SS table is a file. Each SS table consists of blocks, which is a unit of reading and compression. And each block consists of key value records. Mutant stores hot SS tables in the fast disk. Saskatch catches hot blocks in the fast disk. Mirror KV splits the LSM tree into the key and value LSM tree, and it catches hot key SS tables in the fast disk. It also retains hot blocks in the fast disk during compactions. However, the granularity of SS tables and blocks are two cons, because there can be many code records in a hot SS table or block. There are also some works that are record level. SALSM accurately predicts code data with survival analysis and demotes code records to the slow disk. However, the survival module is heavy, and it doesn't support promoting hot records to the fast disk. PrismDB estimates key popularity with the clock algorithm. Hot records are retained in or promoted to the fast disk during compactions. However, the clock bits are indexed by a hash table, which is memory consuming. PrismDB promotes data only during compactions. However, under read-heavy workloads, compactions occur infrequently. In such cases, PrismDB manually triggers compactions to promote hot records, which is inefficient in terms of both promotion speed and I/O overhead. We thus present HotRAP, which performs record level retention and promotion. To save memory, we track the hotness of records with an additional small LSM tree called route. There are two pathways for hot records to reside in the fast disk. Accessed records in the slow disk are inserted into the mutable promotion buffer. During compactions from the fast disk to the slow disk, we consult the hotness tracker route to identify hot records, and we retain those hot records in the fast disk. Hot records in the slow disks are also promoted into the fast disk. We also pick up records in the compaction range from the multiple promotion buffer and promote them into the fast disk. We call this process as promotion by compaction, which is our first pathway. If the multiple promotion buffer gets full due to insufficient compactions, we convert it into an immutable promotion buffer. And we flush it into the fast disk. We call this process as promotion by flush, which is our second pathway. Now let's dive into the details of promotion by flush. When a record is accessed, it is inserted into the multiple promotion buffer. When the multiple promotion buffer gets full, it becomes an immutable promotion buffer. Then we need to convert the immutable promotion buffer into an immutable memory table, and the immutable memory table will be flushed into the fast disk as an SS table later. However, is that safe? Suppose we have a newer version of that record in L1. Then, directly converting the immutable promotion buffer into an immutable memory table will shadow that newer version. That is to say, the reader will see the older version first and returns it before seeing the newer version below. Therefore, we cannot directly convert the immutable promotion buffer into an immutable memory table. Instead, we first check whether there are newer versions in fast disk levels. Only records without newer versions will be inserted into the resulting immutable memory table. Is it safe now? Still no. Suppose we are checking for newer versions. A new immutable memory table is created, and it contains a newer version of K1. If we insert the old version into the immutable memory table later, then it shadows the newer version. So when we convert a mutable memory table into immutable, we need to delete updated keys from the immutable promotion buffer. Now, it's finally safe to convert the immutable promotion buffer into an immutable memory table. Now, let's take a look at route, the hotness tracker of HotRAP. After accessing a key, we construct an access record for it and insert it into route. The access record first goes into an in-memory buffer. When the buffer gets full, it is flushed into the disk like an LSM-tree. We store all its levels on the fast disk. As we can see, most access records are stored on disk, so route is very memory efficient. We update scores during compactions using exponential smoothing. To check the hotness of keys, we only check bloom filters in route so that no disk I/O is incurred. During hotness-aware compactions, we scan hot records in the compaction range and promote or retain them in the fast disk. It only incurs sequential I/O, so it's also efficient. For briefness, we only show the result of a simple experiment here. We compare HotRAP with RuxDB-FD, whose data are stored all in the fast disk, and RuxDB-tiered, which stores data both in the fast disk and slow disk, just like HotRAP. We compare them under the read-only, read-write, write-heavy, and update-heavy YCSB workloads. The results show that the performance of HotRAP is close to RuxDB-FD under the hotspot distribution, because most hot records are promoted to the fast disk. The performance of HotRAP is close to RuxDB tiered under the uniform distribution. The results show that HotRAP incurs negligible overhead. In conclusion, HotRAP performs record-level retention and promotion, so that the space of the fast disk is not wasted. Unlike previous works that track the hotness of records in memory, HotRAP tracks the hotness with on-disk route, which can save lots of memory. Under read-heavy workloads, instead of triggering compactions, HotRAP promotes hot records by flush, which is more efficient. Experiments show that HotRAP incurs negligible overhead under school and non-school workloads. You may read our paper for more details. For example, the algorithm to automatically tune the size limit of route and the cost analysis of route, and the additional evaluation results such as comparisons with other systems, and performance on real-world Twitter traces. For any questions, you can contact the author by these emails. Thanks.